Okay, so for today's deep dive, we're going somewhere truly extreme. I want you to picture this. We're strapping on our virtual dry suits and heading deep, deep beneath the Antarctic ice sheet.
Right, to probably the coldest, darkest, and definitely the least understood part of our entire planet.
Exactly. And people, when you think of Antarctica, you picture this vast, dazzling, white, frozen surface.
Of course, that's the image everyone has. But we're not talking about the surface. We're descending into this crushing blackness underneath the huge floating ice shelves.
Yeah, a place where sunlight has, literally never reached.
Not ever.
So just stay with us for a second. Imagine you're in a tiny submarine, or maybe a little remotely operated vehicle, and you're thousands of feet below that floating ice. The water is barely above freezing.
The pressure is, well, it's almost unimaginable. It would crush a normal vehicle instantly.
And it is absolutely silent. The only thing you might hear is the distant, ghostly cracking of the ice sheet miles above your head.
And down there, you'd expect the seafloor to be, what, like a flat, desolate plain, right?
Totally. You'd picture this smooth, quiet bedrock, maybe gently carved out by an old glacier, and then just blanketed in millennia of fine sediment.
And most of our global maps for a long time kind of reflected that expectation. They showed these relatively smooth, almost featureless contours.
But that expectation, as we're about to unpack from our sources, is just spectacularly geographically wrong.
Oh, completely wrong. What scientists are finding down there, it redefines the entire scale of erosion on our planet. We're talking about these vast submerged valleys, these hidden scars.
Scars that make the Grand Canyon look, and I'm not exaggerating, kind of modest.
Seriously, the Grand Canyon at its deepest point is about, 1,800 meters deep?
Right.
The new mapping efforts are showing these canyons on the Antarctic continental shelf plunging over 4,000 meters deep.
Wait, so that's more than double the depth of the Grand Canyon.
More than double. And they are completely hidden from our view, just masked by kilometers of ocean and the ice sheet itself. It's wild to even think about.
But they aren't just, geological wonders to look at.
No, not at all. They're critical. These giant scars, they were carved by ancient ice, sure, but the real mystery, the thing we need to solve today, is why do they matter to you right now, listening to this? Thousands of miles away.
Because they are the secret, fast-moving highways of the ocean.
That's it. They are conduits, direct pathways that control something truly immense and honestly a little terrifying.
Which is?
The path of warm, deep ocean water straight towards the world's most vulnerable ice shelves.
So that's our mission for this deep dive. We've pulled together two major research findings that are, right now, rewriting our climate predictions. First, we're going to cover this massive mapping effort that found hundreds of these canyons,
forcing us to basically redraw the continent's entire plumbing system.
And second, and this might be even more shocking, we are diving into the discovery of these ultra-fast, almost weather-like events.
Yeah.
We're calling them ocean storms.
Yeah, that's a good way to put it.
They're raging inside these canyons and just dramatically accelerating the melt rate.
And this new science is forcing climate modelers to add these incredibly tiny, fine-grained details into their global models because the stakes, we're talking global sea level rise, are just too high to rely on old maps and old assumptions.
All right, let's dive into it. Okay, let's just start with the stakes because they are catastrophically high, and it all comes down to warm water. We need to introduce the villain of our story.
The villain is this water mass called Modified Circumpolar Deep Water. You can just call it MCDW.
Right. Don't worry about the acronym.
No, just know this. It's deep ocean water that is technically still very cold, but it's maybe 1 to 3 degrees Celsius above freezing. And for ice, that is scorching hot.
And it's a little saltier, which is important, and it carries this immense amount of heat energy.
A tremendous amount. The whole system around Antarctica is basically designed to keep this warm MCDW away from the continent. But the canyons, they're the weak points in the fortress wall.
Before we even get into how the canyons funnel it in, let's talk about what that water is actually attacking. You mentioned this concept, the ice shelf buttress.
Yes, the buttress. The vast majority of the Antarctic ice sheet is not actually floating. It's grounded. It's sitting on bedrock, forming these massive glaciers.
Okay.
The ice shelves, like Thwaites or the Amory ice shelf, are the floating extensions of those glaciers. And because they're still connected, they exert this powerful resisting force. a back pressure.
So they're like a giant cork in a bathtub, sort of holding back all the water, or in this case, the ice behind it.
That is a perfect analogy. They slow the flow of all that grounded ice from the continent into the ocean.
So if this warm MCDW gets in and starts melting that floating shelf from underneath,
The buttress weakens. The cork starts to dissolve.
and when the buttress fails,
The grounded ice accelerates dramatically. And that is the engine of global sea level rise. That's how it happens.
and the most unstable, the most critical part of this whole system is a place called the grounding line.
The grounding line, or GL, that's the exact boundary. It's where the grounded ice sheet finally lifts off the bedrock and starts to float. The point where it goes from being land to being sea, in a way.
And the problem isn't just one glacier melting, is it? It can trigger this huge domino effect. I think the term is marine ice sheet instability.
Yes, MISI. And that is the nightmare scenario for glaciologists.
Why? What is it?
It connects directly to the geology of the seafloor, specifically something called a retrograde slope. Most of the West Antarctic ice sheet sits on a bed that slopes backward. It gets deeper the further you go inland.
Wait, hold on. That feels wrong. If I'm an ice sheet and I'm retreating inland, shouldn't the ground get higher? Shouldn't it get shallower?
It should. And in a stable system, it would. But in West Antarctica, it doesn't. And that's the core of the instability.
So what happens?
Think about it. If the ice retreats just a little bit, the channel it's sitting in suddenly gets deeper and wider.
Oh, I see.
This means more of the ice front is exposed to that warm, deep water, and a larger column of water is pushing up on the ice, applying more buoyant force.
So retreating just a little bit exposes it to even more of the thing that's making it retreat in the first place.
Exactly. Retreat leads to more melt, which leads to more retreat. It is a self-perpetuating, unstoppable process once it really gets going. The geometry of the seafloor itself makes it irreversible.
That's terrifying. And this is why the stakes are so high. If the entire West Antarctic ice sheet goes, which is so vulnerable because of this mechanism, what are we talking about in terms of sea level rise?
The estimates are up to 3 meters globally.
3 meters. Let's put that in context. 3 meters isn't just wet feet at high tide.
No.
That's hundreds of billions, maybe trillions of dollars of coastal infrastructure gone. It would redraw the map of entire countries. Major port cities like Shanghai, New York, Amsterdam. They become fundamentally different places.
It's a global crisis, not a regional problem.
And the canyons are the catalyst. We can already see this happening, can't we? The sources point to Pine Island Glacier and Thwaites Glacier.
Absolutely. Pine Island Glacier, or PIG, has seen its grounding line retreat up to 31 kilometers between 1992 and 2011.
31 kilometers. Wow.
And that retreat is driven almost entirely by this warm MCDW flowing directly through these deep submarine troughs that act as perfect funnels pointing right at its base.
So it's like finding a massive leak in a dam, but the leak is actually a river of warm water that's actively melting the dam from the inside out.
And the whole dam is built on a backward-sloping, unstable foundation. The canyons are the direct pathways. They channel the heat right to these critical grounding lines. If you don't know the plumbing, you can't predict the flood.
Which brings us to the next big problem. To understand the flow, you have to have a map. And for a long time, we just didn't. This has been called the Cartography Catastrophe.
It really was. I mean, if these canyons are so massive, how on earth did we miss them for so long? Because the Antarctic continental shelf it's the definition of inaccessible real estate. You have year-round sea ice, you have constant storms, it's incredibly remote. Just dropping an echo sounder into the water to map the bottom is a monumental task.
So we have this massive data deficit. We've basically been guessing the map of one of the most critical environments on the entire planet.
We absolutely have. Take Prydz Bay, for example. It's home to the enormous Amory ice shelf in East Antarctica. Our sources say that in some of the most crucial areas there, less than 5% of the seafloor is mapped by direct soundings.
Less than 5%. That's basically nothing. It's like trying to navigate New York City, but you only know what 5% of the street corners look like.
An impossible task. So for the other 95%, the climate models had to fill in the gaps.
How do they do that?
They rely heavily on interpolation, basically guessing what's between two known points, or satellite gravity estimates. They measure these tiny, subtle differences in Earth's gravity field that might suggest a big depression or mountain range under the water. But it's fuzzy, it's low resolution. It leads to what the sources call massive uncertainties.
And there's the core problem. If I don't know the exact depth and shape of the seafloor, If I don't know the geography, I can't accurately simulate where the warm water is going to go.
You can't. The geography of the seabed is the single most important factor regulating where the heat goes. And a guess is just not good enough when you're talking about billions of tons of ice loss and 3 meters of sea level rise.
That really sets the stage for what had to be this incredible scientific adventure. The mission was simple, but, Herculean.
Hmm.
Map the hidden highways.
Right. Move past the data deficit. And they did it with this updated project, the International Bathymetric Chart of the Southern Ocean, or IBCSO V2.
So this wasn't just one ship sailing around for a year.
Oh no, this was a massive international effort, combining decades of data from every source you can imagine. Seismic surveys, old naval charts, ice-penetrating radar from planes, historical ship tracks, everything.
Okay, let's talk about the scale of this discovery, because the results are just staggering. What did they find? How much of the Antarctic margin is actually carved up by these canyons?
They successfully identified 332 complete canyon networks.
Wow.
And within those, 3,291 individual canyon segments.
So just to put that in perspective, how does that compare to what we thought was there before?
They found nearly 5 times the number of canyons that had been identified in the last big comprehensive study. This wasn't just, tidying up the map a little bit.
No, this was fundamentally redrawing the geology of an entire continent's margins.
Exactly. But it's more than just geography. The canyons themselves are like these fossil records etched into the seabed. They tell us the story of how the ice has behaved in the past.
They're like a deep ocean time machine.
They absolutely are. The researchers looked at the geomorphometry, the shapes and the measurements, and they found those really striking differences between East and West Antarctica.
Okay, so paint a picture for us. What does an East Antarctic canyon look like compared to one in the West?
In the east, the canyons are, they're more complex, they're longer, they have more branches, and they tend to be U-shaped.
U-shaped. That's the classic sign of a glacier.
The classic signature of slow, persistent, massive glacial erosion. The East Antarctic ice sheet is ancient. It's about 7 million years older than the one in the West. So its canyons reflect this long, continuous scouring by huge, slow-moving rivers of ice.
Okay, so the canyons in West Antarctica, home to the super vulnerable Thwaites and Pine Island glaciers, they must look different.
They do. They're generally shorter, much steeper, and they tend to be V-shaped.
A V-shape, what does that tell us?
A V-shape suggests sharper, maybe faster, more focused erosion. It could mean that when the warm water does get in, it moves more aggressively and efficiently through those channels compared to the wider U-shaped canyons in the east. It suggests a history that's more dynamic, maybe more prone to rapid change.
That's critical. Well, so the shape of the seafloor itself could be telling us which areas are better at delivering that warm water payload right now.
Precisely. And speaking of decoding history, let's pivot to this other incredible part of the quest. Scientists tried to figure out what the ocean was actually doing during the last ice age.
How?
By using sediment cores. This is a field called paleoceanography, and it's like ocean detective work, reading ancient chemical signatures from deep mud.
Okay, so they drill down to the seafloor and pull up these long tubes of mud.
Yep. They analyzed 9 of these cores, pulled from crushing depths between 2,200 and 5,000 meters. And they were trying to figure out the origin and the age of the deep water from tens of thousands of years ago.
How do you tell the origin of water that disappeared millennia ago?
You use trace metals, specifically the isotopic signature of a metal called neodymium, or ND-Day. And this is where we need our analogy engine to kick in.
All right, let's have it.
Okay, think of a sediment core, like a massive frozen layer cake that's been sitting untouched for 20,000 years.
Okay, I like it.
Every centimeter you go down that core is a time slice, a layer of geological history. Now, the neodymium isotope, that's like a permanent, unforgeable fingerprint.
A fingerprint.
Yeah, different land masses, different ocean basins, they all have a unique chemical ratio of neodymium isotopes that dissolves into the water. When tiny particles settle out of that water and get buried in the sediment, they carry that N fingerprint with them.
That is fascinating. So you can look at the fingerprint in a slice of cake from 15,000 years ago and say, ah, this water came from the North Atlantic. Or in this case.
Or in this case, this water was locally sourced and completely stagnant. That's what they found. In the layers from the last ice age, they found an exotic isotopic signature, a fingerprint that doesn't exist anywhere in the modern Southern Ocean. It was so weird they initially thought their equipment was broken.
Why was it so weird? What did it mean?
That signature could only form if the deep water stayed almost completely motionless for a very, very long time. It wasn't mixing. Its chemical signature became totally unique and localized.
So it was like a massive trapped pool of ancient water.
A huge carbon-rich body of deep water that was just stuck sitting at the bottom of the ocean for millennia.
A deep ocean time capsule, full of carbon.
Okay, we have to hold on to that idea because that is a critical link to what's happening today.
It really is.
But before we get to the carbon bomb, let's fast forward to the present day. Because the movement of the ice isn't just a long-term problem, it's happening hourly.
That's right. That grounding line, that crucial boundary, it's not stable over decades. It moves in real time with the tides, twice a day. So scientists needed a way to track that dynamic hourly movement. And that's where this DRT method comes in. Differential range offset tracking? Sounds very technical.
It is, but the concept behind it is just brilliant. It uses high-resolution radar satellite images to measure the subtle vertical movement, the flexure of the floating ice shelf as the tides go in and out.
Okay, analogy engine time again. How do we visualize DRT?
Let's use a daily life analogy. Imagine the entire floating ice shelf is like a giant floating dock that's attached to the shore.
Okay, I can see that.
When the tide comes in, the water lifts the edge of the dock up. The point where it starts lifting off the bottom, that's the grounding line. DRT works by taking two super high-resolution pictures very close together in time, and it measures that tiny vertical bend.
So it's measuring the subtle flexing of the dock as the tide swells under it. And that tells you exactly where it's floating versus where it's still touching down.
Precisely. And they use this on the Amory Ice Shelf in East Antarctica. What they found about the size of the grounding zone, the area where the GL migrates back and forth, was just shocking.
How big was it? Previous studies thought maybe a few hundred meters, right?
That was the assumption. The results were dramatic. They found the migration zone can vary from a few hundred meters up to an astonishing 14.2 kilometers in a single year.
14.2 kilometers. That's almost 9 miles.
Just from tidal movement. In 1 year. Previous models were underestimating this dynamic instability by orders of magnitude.
That's not glacial stability. That's like breathing. The whole boundary of the ice sheet is shifting by miles just because of the daily ocean cycle.
And they didn't just measure the shift, they actually categorized the movement into 3 distinct modes depending on the shape of the bedrock underneath.
Okay, what were the modes?
First was the linear mode, simple, proportional. For every 1 meter increase in the tide, the grounding line moved about 3.1 kilometers upstream. A nice, predictable ratio.
Easy for the models to handle. What was the second mode?
The threshold mode. In this case, the grounding line stays put until the tide hits a certain height. It's like it's stuck on something. At one spot, the tide had to get over 0.95 meters before any real movement happened.
So it's like a temporary anchor that only breaks free when the buoyant force gets strong enough. Okay, what about the third one? The asymmetric mode. That sounds worrying.
It is. This is where the physics gets uneven. In this mode, the upstream retreat during high tide is significantly larger than the downstream return during low tide.
Wait, say that again? It moves further inland on the high tide than it moves back out on the low tide.
Exactly. The high tide is overpowering the low tide's ability to reground the ice shelf. It creates a net drift inland.
So even within a normal, healthy tidal cycle, the ice sheet has this natural bias towards retreat.
That's the critical takeaway. It shows high tides are the dominant driver, providing a net mechanism for the grounding line to just creep landward over time.
So you can't just measure the average movement. You have to capture the peaks, because that's when the irreversible change happens.
Exactly. And the DRT study also found these critical things called pitting points.
What are those?
They're local spots where the floating ice shelf touches down on an underwater mountain or ridge. They act like underwater moorings, providing crucial buttressing force.
And are they stable?
Not at all. They're very sensitive to the tides. Using DRT, they found 11 of these on the Amory ice shelf, including 6 that had never been mapped before, and they measured how their contact area fluctuated. One point went from 170 square kilometers of contact to 289.
Wow. Hundreds of square kilometers of physical connection to the seabed just turning on and off with the tides multiple times a day. That is a massive difference in how much the ice sheet is being held back. Okay, let's connect this incredible hourly detail back to the ancient past. That strange, exotic fingerprint they found in the sediment cores. This evidence of a huge stuck carbon reservoir during the Ice Age.
Right, so let's go back about 12,000 years to the end of the last ice age. As the planet started to warm, The Antarctic bottom water, that's the super cold, dense water formed around Antarctica, it began to expand.
And this was driven by a couple of things, right? Less sea ice and more meltwater.
Exactly. And the meltwater is key. It lowers the salinity of the surface water.
Okay, so it makes it less salty. Why does that matter?
Because salinity is the main driver of density in the deep ocean. The newly formed bottom water, while still cold, was slightly less salty and therefore slightly less dense than the water that had been sitting there during the peak ice age. And that slight change was enough to destabilize the entire deep ocean structure.
So this new, slightly less dense water starts moving around. What's it pushing out of the way?
It displaced that enormous reservoir of deep, carbon-rich water we talked about, the stagnant stuff that had been sitting motionless for millennia.
The time capsule.
The time capsule.
Yeah.
And because it was so stagnant, it had been collecting a tremendous amount of dissolved carbon dioxide from decaying organic matter, all locked away from the atmosphere.
So when the new, lighter water moved in,
Yeah.
it basically cracked open the time capsule and caused it all to mix.
It's like opening the lid on a giant bottle of soda that's been sitting and collecting gas for 10,000 years.
And all that stored CO2 rushed back into the atmosphere.
It did. And this massive natural release of stored carbon is now thought to have been a significant contributor to the global warming that finally pushed the planet out of the last ice age.
That's profound. The deep ocean circulation around Antarctica literally helped dictate how fast the entire planet warmed up. And that serves as a huge warning for today.
It absolutely does. Our sources emphasize that over the last 50 years, the deep ocean around Antarctica waters deeper than 1,000 meters has warmed significantly faster than the global average. We are basically repeating the scenario.
We're increasing meltwater, we're warming the deep ocean.
And we know what that combination can do. Understanding how the ocean responded back then is vital for grasping what might happen today as the whole system changes again.
Okay, so we've mapped the massive highways, the canyons, we've decoded the ancient history of the carbon bomb. But mapping the highway doesn't tell you about the traffic on it. Now we need to zoom way in to see the cars that are actually carrying the heat.
And that brings us to the second huge discovery from our sources, the ocean storms. This is where we go from a geological scale of 4,000-meter canyons down to a weather timescale.
We're talking about sub-mesoscale ocean features. What on earth are those?
They are basically eddies and vortices in the water, but they're tiny, just 1 to 10 kilometers across.
So they're not like big ocean currents.
No. If the big ocean currents are like the jet stream in the atmosphere, these are like localized storm systems. Think of them as miniature underwater hurricanes or tornadoes. They only last for a few days or even just hours.
But they're happening right up against the ice front.
Exactly. And they pack a massive kinetic punch. Researchers use high-resolution models and observations, and they found that these little storms are the immediate hyperactive drivers of melt at places like Thwaites and Pine Island.
So what's the damage report? How much of a difference do these tiny fleeting storms actually make?
They cause melt on a weathered timescale, not a seasonal one. This is a fundamental shift in how we have to think about this. These storms shoot in under the ice shelves, and they account for nearly 20% of the total melt variation over a whole season.
1/5 of the seasonal melt is being caused by these little hyperactive features.
Yes. So if your model ignores these storms, your calculation is missing a huge piece of the puzzle.
What happens during a peak event, when one of these storms really hits the ice?
The melt rate can increase by as much as threefold within a matter of hours.
Threefold. In hours. That's incredible. So what we think of as an average melt rate is really just a series of these rapid-fire extreme events.
That's right. And here's the kicker. It's not a one-way street. They found a positive feedback loop. The melting itself creates these unstable fronts of fresh water right at the ice face, and these unstable fronts actually intensify the ocean storms.
So wait, melt creates stronger storms, and stronger storms create more melt.
You got it. It is a runaway engine happening on a daily, even hourly basis, hidden miles beneath the ice.
And this makes places like Thwaites, which we already know is a huge global concern.
A sub-mesoscale hotspot. The processes that last only a few hours are fundamentally changing the stability of the entire system. We can't rely on models that just average everything out anymore.
And this all just brings us right back to the beginning, back to the maps. We know the ice is being attacked by these chaotic hourly ocean storms.
Which are themselves being channeled by these massive hidden canyons.
So if our map of the canyons is wrong, our prediction of where the storms are going to hit is wrong.
And our sea level rise projections are completely unreliable. We can see the real-world impact of this cartography catastrophe in this one specific study from Prydz Bay in East Antarctica.
So what did they do? They took an old, inaccurate map, swapped it for a new, corrected one, and reran their ocean model.
Exactly. They wanted to see what changed. And the core correction was a big one. They found this new depression, a big topographical feature on the seafloor, that was up to 500 meters deeper than anyone had assumed.
500 meters is not a small error. That's like realizing a whole canyon was much deeper than you thought.
It's a huge change. And it meant this depression was acting as a major unmapped pathway for a coastal current there.
So what happened when they plugged the correct map into the simulation?
The change was drastic, and this is where it gets really interesting because it was totally counterintuitive. With the correct map, the model showed a marked decrease in the amount of heat getting to the massive Emery ice shelf.
A decrease. By how much?
The heat transport went down by 18 to 22%, which meant the calculated melt rate for the Emery ice shelf dropped by about 13%.
So the old wrong map was actually overestimating the melt for Amory by billions of tons of ice per year.
Oh.
That sounds like good news.
For Amory, yes. But here's the paradox, and this is why the geography is so critical. The heat didn't just vanish. It shifted. Because the circulation changed with the new map, the warm water just went somewhere else. The study found that the melting of the nearby west ice shelf was enhanced. It increased by almost 19%.
Wait, so correcting the map didn't solve the melt problem, it just moved it down the coast to a different glacier.
Exactly. If you use the wrong map, you might be predicting the right total amount of melt, but you're predicting it for the wrong place. And the difference between a slightly wrong map and a corrected one can mean billions of tons of ice melt shifting location, which completely changes our understanding of which regions are stable and which are not.
So is the problem the heat itself, or is it the plumbing?
It's both. The heat is coming from global deep ocean warming. That's the crisis. But the geometry, the plumbing of the canyons, determines which specific ice sheet hits that irreversible tipping point first.
Yeah.
You can't model the impact without knowing the exact route the heat will take.
Okay. We've gone from 4,000-meter deep ancient scars to these chaotic, hourly, kilometer-wide storms. As the expert here, just synthesize this all for us. What is the big takeaway?
The thing that's so fascinating is that the fate of the entire Antarctic ice sheet is governed by these systems that operate on wildly different scales, but they're completely interlinked.
Right.
You have the massive hidden canyons. They're the geological highways that channel the bulk flow of warm water. And then you have the tiny ephemeral ocean storms. They're the hyperactive drivers that deliver that heat right to the grounding line with this extreme short-term volatility.
And with the deep ocean warming so fast, understanding these tiny high-frequency events it's incredibly urgent, especially when we remember how past changes in the deep ocean led to massive carbon release.
Exactly. To get accurate projections for sea level rise, we can't rely on models that smooth out this vital detail. We have to incorporate these weather-like processes. And that means we need new tools, new ocean-going robots that can capture these fleeting kilometer-scale events right where the melting is actually happening.
It's just astonishing. We started this deep dive talking about geological features 4,000 meters deep, and we've ended up learning that processes just 1 to 10 kilometers wide, lasting only a few hours, are moving the grounding lines of the planet's largest ice sheet by kilometers in a single day.
And here's the final thought. The greatest physical force on Earth, the Antarctic ice sheet, is being dismantled, not by some continental scale hammer, but by an army of tiny, hyperactive waves. That's the kind of complex, multi-scalar problem we are racing to understand.
That is a powerful place to end. We've seen how the deep past and the minute-to-minute present are governing the future of our coastlines. It's a reminder that the biggest threats are often driven by the things we can't see, operating at the smallest, hardest-to-measure scales. Thank you for taking this deep dive with us.
Remember that complexity? The canyons are the map, the warm water is the fuel, and the ocean storms are the matches. We'll see you next time.